Alright, gentlemen, here we go again with the Z80 Funtime. Welcome back to the old computer shack. Alright, so, as we mentioned yesterday, we have a ROM, a 28C64, and a RAM, a static RAM, a UM6116. And, we need to interface both of these to the Z80 processor. Now, when we reset the Z80 processor, as you recall from previous Z80 Funtime videos, it begins executing at address 0. That is the reset vector, 0. It fetches an instruction from address 0 and evaluates that instruction. And it just keeps doing that. So, obviously that means that we need to put this 8K ROM in the bottom of the Z80's memory map. That would be from 0 to what? 1FFF, I think? Yes? Yes, I think so. I may not be able to do hexadecimal math in my head right now for various reasons. So, then above that, we'll have to map in this 2K ROM. And the reason I'm using a 2K ROM is because I happened to have it in the drawer. This is one of the chips that we salvaged off of those gas pump controller boards. So, the plan here is to just write some simple software and burn it to the ROM that just makes some I/O requests so we can see that everything's working. And technically, we could probably do that without any RAM. We could just write some assembler, some Z80 assembler, and assemble it and burn it to the ROM and just do everything in registers and not fuck around with needing this RAM. But perhaps I'm in the minority by saying this, but I vastly dislike assembly language. I think it makes code difficult to read, difficult to debug, and most importantly, unportable. So what I always try to do when possible is write all the code that I can in a higher level language such as C. C is a fairly low level, high level language. You can kind of see in your brain face what the assembly language is going to look like that the C code that you're writing kicks out. You know what I'm saying? That makes it pretty good for like this hardware biting stuff. You know what I'm saying? And we'll use SDCC, the small device C compiler, for that. I'm getting off on a tangent. What was I talking about? Yes, so I'm pretty sure that SDCC is going to need at least a little bit of RAM to initially set up its stack and call its way into the main function. So that's the reason we've got this 2K RAM chip in here. And so what we want to do is we want to map this 8K ROM into the lowest address space of the Z80, and then we want to map this RAM in there somewhere. We can use compiler directives to tell it where the different memory segments are, the ones that are writable and the ones that are not. I need to do a little more research on that and to make things happy. So we're going to do that address decoding with our 74LS00 quad 2-input NAND gate. And so before we get into that fun stuff, perhaps it would behoove us to talk about digital logic gates, which I'm sure most of you will find boring as fuck because you probably already know all of this stuff, but just to make sure that we're all on the same page so that we can have Z80 Funtime together, I think that I should spend one video doing this, and I sincerely hope that I'm capable of doing that this evening. Alright, Digital Logic 101. As you all know, Digital Logic runs on magic smoke. The magic smoke gets pressurized through tubes that we call wires, and at 0 volts the magic smoke is at negative pressure, and at 5 volts the magic smoke is at a positive pressure. So we call this, when the magic smoke is depressurized, we call this a 0, and when the magic smoke is pressurized inside of the tubes, we call it a 1. So we have all of these logic gates that can act upon these various pressures of magic smoke in various ways. The most simple probably being the buffer, which we will draw on a schematic like this. This is a buffer. Buffoir. So we have an input, one input, and one output. And all this does is it takes, if it has a 0 on the input, it puts a 0 on the output. If it has a 1 on the input, it puts a 1 on the output. Hot shit, right? You're probably asking yourself, what the fuck is the point of this dumb bullshit? Well, a lot of chips, specifically certain CMOS chips like we have on this breadboard up here, are not capable of sourcing a whole fuck ton of current. So we can use buffers like this to interface these kind of anemic, like current source-wise, CMOS chips to the big bad analog world. So like these buffers, you know, allow the circuit to sink a whole shit ton more current, drive a whole lot more devices out there on the bus. So that's all happy and good, right? The next gate we should talk about is probably the inverter. It looks very similar to a buffer, except it's got a little nut on the end of it, right, like that. That's an inverter. That little circle always, wherever you see this little circle on these logic symbols, always means inversion. Anything that goes into this circle comes out the other way. So if we put a 0, this is the input and the output of our inverter. If we put a 0 into the ass end of this inverter, it pukes out a 1. That is, if the magic smoke is unpressurized on this end, this black box device pressurizes the magic smoke in this end. And vice versa, if the magic smoke is pressurized on this end, then this magical black box device depressurizes the magic smoke on the other end. Happy day. Alright. Now these devices only have one input. We have other devices, logic gates, oops, wrong way, that have two inputs. Let's talk about an AND gate. This is an AND gate. It has two inputs and one output. We'll call this N1 and we'll call this N0 and N1. And it has an output right here. So, we'll call this A and B actually, then we won't get confused. Alright, so we can write truth tables similar to these single input devices here, except they're a little bit more complicated because we have several different, each of these inputs can be a 0 or 1. So we've got several different inputs we can have. We can have our A and our B, right? We can have them both 0. We can have B being 1 like that. We can have A being 1 and B being 0 like that. And we can have them both being 1 like that, with the magic smoke pressurized in both. Then the output, in this case, the AND, only goes high if both A and B are asserted. That is, they both have the magic smoke pressurized. Otherwise, the output will have the magic smoke depressurized. There's our AND gate. Pretty snazzy, right? Another basic logic gate we can talk about is the OR gate, and we'll draw it like this. It looks kind of like a Star Trek communicator. It's some pretty hot shit, isn't it? Alright, so we have our A and our B inputs, and we have our output. Like so. Alright, and we can do the same kind of truth table with our OR gate right here. We have our A and our B inputs of different values here. Right? And our output in these cases will be high if A or B has the magic smoke pressurized. So if A or B, so in this case neither A nor B have the magic smoke pressurized, so our output will be depressurized. In this case down here, B is pressurized, so since A or B, right, yeah, okay, here A is pressurized, A or B, okay, and here they're both pressurized, so, we'll output a 1 there because, one or the other is still pressurized. Hot shit, right? Oh yeah, boy, we're doing some learning now. And there's another basic logic gate, which you won't see very often unless you get into the, nitty-gritty insides of CPUs and shit and start making adders and bullshit like that. Or a little bit of, sometimes video circuitry uses these for various purposes. But we have the exclusive OR gate, which is kind of like an OR gate, except it's kind of like putting something out the back there somehow, right? So we've got our A and our B inputs here, and our output. And the exclusive OR gate is like an OR gate, except it only outputs true, that is, pressurized magic smoke, if A or B, but not both, of the inputs are pressurized. So the truth table for it would look something like this. Alright, so this would be a 0, neither are pressurized. With both pressurized, we only want one or the other, so that's going to be a 0, but when they're one or the other are pressurized, the magic smoke comes out pressurized, like so. Are you having fun yet? Are you learning shit? Are you, elucidated and stuff? Now, shit gets even more fascinating. Alright? Let's talk about NAND and NOR gates. Alright, remember the little nut on the end of our inverter, meaning that whatever goes through that nut gets changed. You know what I'm saying? We can draw a NAND gate that is NAND. This is an AND gate. This is an OR gate. I probably should have labeled these. This is an XOR gate, exclusive OR gate. This is a buffer. And this is an inverter. Alright. Let's talk about that NAND gate that I got off track of. So, a NAND gate is very much like an AND gate, except it's got a nut on the end, the same as the inverter. So, there's our AND gate with a nut on the end. It's got an output, and it's got two inputs, A and B, and that's not supposed to be there. He has a birth defect or something. Don't worry about him. So, how do you think this is going to work? Well, as you've probably guessed, it's going to be exactly like an AND gate, except since the output of this AND gate is going through this inversion nut, whatever comes out is going to be backwards from how the AND gate is. So we have our A and our B inputs, like we had before, right? And our output is going to be totally backwards. Our output from our AND gate gets inverted down here, so it's going to be 1, 1, 1, 0. Alright, and there's also a NOR gate. This is a NAND gate right here. We also have a NOR gate, and you've probably guessed what its symbol looks like, haven't you, my friends? That's not a very good NOR gate drawing. You will have to pardon me. I am not an artiste. Alright, what do you think that's going to be based on the truth table from our previous shitteroo there? Yes, that's right. A and B and our output are going to be completely opposite of the OR gate, because the output of the OR gate's gone through this nut and getting inverted. Alright? So that's going to be 1, 0, 0, 0. All right. Now, I don't think there's any X NOR gate. There probably is, but nobody ever uses them for anything, so don't worry about that. You'll probably very seldom use an X NOR gate. So, now that you have learned all about basic logic gates, let's talk about why NAND and NOR gates are special as fuck. It so happens that you can make any other gate out of a NAND gate or a NOR gate just because of the way that they are. It's magic. It's sweet as fuck, right? So let's say we want an inverter. Alright, we can make that out of a NAND gate. How are we going to do that? Well, we might take our input and send it into both of the inputs of the NAND gate like this. Alright, we have our input and our output, right? So, looking at the truth table of the NAND gate over here, we can see that when A is depressurized, the magic smoke is depressurized, both the A and B inputs here on the NAND gate are going to be low, and the output will be 1. Right? Likewise, when the single input here goes high, both the A and the B inputs of the NAND gate will go high, and the output will be a 0. Fancy shit, right? You want to make a buffer out of a NAND gate? You just string two of these together in a series, right? So it inverts it and then it inverts it back. Now, here's where shit gets really interesting. We can make OR gates out of NAND gates. Alright, so let's consider this schematic symbol right here. Alright, we'll draw an OR gate, and we know the truth table of the OR gate. We've already figured that out up here. But instead of fucking around with this, remember this NOR gate where we inverted the output? Let's instead invert the inputs. Alright, so we have our A and our B inputs. A and B, 0, 0, 0, 1, 1, 0, 1, 1. And we have an output. Now, okay, when A and B are both low, alright, those signals go through these little nuts on the input of this OR gate here, so those will both be pressurized. They'll both be true. And what happens when both inputs to an OR gate are turned on? We get a 1. Alright? Likewise, if A is off and B is on, they get inverted by these nuts, so A becomes on and B becomes off, and we get an output of 1. Alright? Now, likewise, when A is on and B is off, it gets inverted, so A is off and B is on, A is off and B is on, and the output will be 1. And when both A and B are pressurized, the magic smoke is pressurized, I should say, those two inputs will be inverted to zeros. And remember what happens with an OR gate when both of the inputs are 0. The output is 0. Now compare this truth table right here with this truth table over here from this NAND gate, and you will see that they are completely identical. This weird OR gate with the nuts on the input is the identical gate to this NAND gate with the nut on the output, and likewise the same applies to NOR gates. You can also redraw a NOR gate as an AND gate with nuts on the input, like that. Alright, so this allows us to do some interesting shit. Let me get another sheet of paper. this property of NAND gates, and we always tend to use NAND gates for this because they're the cheapest gate, or at least they were back in like the olden days. NAND gates have fewer components on the chip than any of these other gates, and you can make any other gate out of NAND gates or NOR gates like this. You can even make exclusive OR gates out of them. We can explore that later. It actually takes 4 of them. It's kind of complicated, to be honest with you. I can't remember how to do that off the top of my head without doing some scribbling. So, I'm sure you don't want to fuck around while I head scratch about that. Alright, so this property of NAND gates, this is also a NAND gate right here, and this is a inverter via a NAND gate, built via a NAND gate. You know what I'm talking about. So, this allows us to do some interesting shit. A lot of the times, in digital logic circuits, we have to take some signals, you know, if this signal is on, or this signal is on, or this other signal is on, or this other signal is on, then if either of those two states are true, then we want to do something, right? And we can do that very interestingly with NAND gates. Like we can say that if we can do stuff like that we normally have to use 2 gates for, 2 chips for, to have both and OR gates, because you know you don't get the and OR gates on the same chip, right? Let's say we have a circuit that looks like this, all right, and we want to go into an AND gate, right? And then we've got a C and a D input, and we want to go into another. Let's use an OR gate, otherwise it doesn't make any sense. So, sorry, I'm dumber than fuck. And then that goes into an AND gate, and we've got an output. So if A or B and C or D are asserted, then the output will be asserted, right? So this would normally take, I mean, you get 4 2-input gates on a 74 series logic chip. So normally you'd have to have 2 separate chips to do this shit. Very inefficient space-wise and money-wise, right? But since we can draw our gates in funny ways, right? We could do this circuit right here with NOR gates. Remember, a NOR gate will invert the output like that, but then we can also redraw the NOR gate like this, with nuts on the input like this, right? So the signal goes through here, it gets inverted, but before it goes into this AND gate, it gets reinverted right back to what it was to begin with. So here we can do the same thing with a single chip that we would have had to have used like 2 chips for up here. So that's going to be part of the basis for our address decoding for our RAM and our ROM up here in the Z80 Funtime space thing. Right, let's talk about how we want to interface the ROM and the RAM to the Z80's address space. The ROM and the RAM to the Z80's address space. So the ROM has to be in the lowest part of the Z80 address space. So let's draw, this is the Z80 address space, and it starts at 0 and it goes up to FFFF, right? Oh, sorry, I didn't have you on the camera there, right? So we want to map this 8K ROM down here in this part, right? And then we have a 2K RAM that we want to map right above this 8K ROM, or we don't necessarily have to. We could map it any fuck where else we wanted to. But it just so happens that we can easily map it right above this 8K ROM. Right. Well, our 8K ROM is going to have, how many address lines? 13, I think. Right? Does that have an A12 on it? My writing is so shitty that I can't 12. Yeah, A12, yeah. So an 8K ROM will have 13 address lines on it. Alright, so A0 through A12. Alright, and we'll hook those straight up to the ROM. Alright. Then we have, oh, that's supposed to be A12. Alright, then we have A13 right above here, alright. So, if A13 is low, that'll indicate this lower 8K space in the memory map, and if A13 is high, that'll be pointing to this upper 8K space in the memory map, of which the 2K ROM will occupy a part of. Now, this is partial address decoding. You won't see partial address decoding in very many modern systems because with the advent of things like programmable logic and stuff, it's very easy to, design circuits that don't benefit from partial address decoding. But back in the day, this was very common. Like for an embedded system that would never be expanded, it didn't matter if some of the shit was mirrored in the memory map, right? So here's an 8K space. Alright, here's another 8K space, right? So our 2K ROM isn't going to have A0 through A12. It's only going to have, A0 through A10, right? Did I do that right in my stupid head? Yes, I did, I think. So only A0 through A10 will connect to the RAM. Alright, A11 and A12 we don't give a shit about, right? We don't give a fuck what A11 and A12 are, but when A13 is high, we'll know that we want to access this ROM. And the side effect of this is that this 2K RAM is going to get mirrored 3 more times up here through this memory map. Alright, so let's see, I guess the first byte of the 2K RAM will be at hex 2000, right? I think? Yes. So if we fuck with the byte at hex 2000, we'll get the first byte of that RAM. If we fuck with the byte at hex 2001, we'll get the second byte of that RAM. Now, likewise, if we fuck with the byte at what? 2800 hex, we'll get that same first byte of RAM in this space right here, right? If we fuck with the byte at 3000 hex, we'll get the same first byte of RAM in this space up here. And if we fuck with the first byte of RAM at, oh god, I'm too dumb to do math in my head, but you get what I'm saying, right? So the 8K ROM goes from 0 up to 1FFFF, and this RAM space then goes from 2000, right, up to 27FF, right? And then it gets mirrored again from 2800 hex to 2FFF hex, and it gets mirrored again from 3000 hex to 3FFF hex, and it gets mirrored again, no, I did that wrong, to 37FF hex, and it gets mirrored again from 3800 hex up to 3FFF hex. Now, you might think that this would be a problem, but it actually isn't. As long as we inform our compiler or assembler where these segments occur in the memory map, it'll know not to generate code that fucks with these mirrored memory areas here. And since we're also completely ignoring A14 and A15, we don't give a shit what they are in either case here. We don't give a shit about what those are in either case. That also means that this whole 16K block right here, containing the RAM, containing the ROM and the mirrored RAM, will also be mirrored up through the memory map itself 3 more times. Right like that. Okay, but since this is just a stupid breadboard computer that we're not going to be making expansion cards for and shit like that, it doesn't matter one lick that all of this funny mirroring stuff is going on, as long as we inform our compiler or assembler to only fuck with that first 8K segment, or that first 2K segment, or the 2K segment immediately following that 8K segment. This first 10K segment, we should say, our code will work just fine. So this is what the memory map of our initial excursion into the Z80 Funtime is going to look like. And the way that we will do this is entirely with... What did I do with my pen? Ah, a pox upon thee, curse of the grape. I think I may have a problem. Oh well. We're going to do all of that address decoding with a single quad 2-input NAND gate. And how are we going to do that, you ask? I'm glad you asked. We can do all of that using the A13 line, only the A13 line, and recall that when the Z80 CPU, remember when we examined the Z80 CPU and looked at all of the pins on it in a previous video, it has a memory request line, MREC, down here, which is active low, that specifies when a memory cycle is going on, as opposed to an I/O cycle. Right? I/O cycles are specified by this I/O request line being asserted. It's also active low. So that's for like reading the keyboard and writing shit to the screen and stuff, or to the serial port or what the fuck ever, right? But when we're accessing memory, when we're accessing RAM, it asserts this memory request line down here. An active low line. It's always high, but when it's doing a memory cycle, it goes low. The magic smoke gets depressurized in that line, right? So we have to take both of those into account. We can't just use A13 by itself. Otherwise, when we try to do I/O cycles later on, with our serial I/O chip and all of that shit, we'll have all kinds of trouble. So we do have to take the memory request line into account. So what we'll do is we'll take the memory request line, and remember it's active low. It goes low when there's a memory cycle in progress. All right, and we'll take our A13 line, right? That we get to that's going to be selecting between which of these 8K segments we're looking at, right? A13, recalling our binary arithmetic, which I really can't do in my head, so I shouldn't be like acting like I can, because that's just dumber than shit. So first of all, before we do anything, we've got to invert this memory request line so that it's actually high when there's a memory cycle going on, because that'll make it a fuck ton easier to use with AND gates. So we can do that, remember, we can do that with a NAND gate by making an inverter out of a NAND gate. So we'll take this memory request line, we'll feed it into a NAND gate, just like this. Alright. Very good. Now we have a signal that's high when a memory cycle is going on, and low, that is, the magic smoke is depressurized when a memory cycle is not going on. Alright, so then we need to select between whether A13 is low or high, and we have to AND these together in various ways. So when A13 is low, right, that's going to indicate that we want to access this ROM. Alright, so since the chip select on both the ROM and the RAM is also an active low, we want to have a low output when that happens. Fortuitously, this is easy to do with NAND gates. So we'll put A13 through another inverter that will make out of another gate on this this quad 2-input NAND chip. Alright, so now when A13 is low and memory request is also low, and remember, and when those are both low, we want an active low signal indicating that we want to access the ROM. Fortuitously, that nut on the end of this other NAND gate is going to give us that active low signal, so we can call this ROM chip select, and it's active low. That's what the bar on the top indicates. Likewise, when A13 is high, we can pull it off of here and go up here somewhere like this, and when memory request is asserted, meaning it's low, and then it gets turned high by this inverter that we've made here, we can take the signal off of here. When both of these are true, when a memory request is in progress and A13 is high, right, then we want to have an active low RAM chip select. Right, so we can do all of our decoding, our partial address decoding for our swank shitty ass breadboard computer, using a single quad 2-input NAND gate, a 74 LS00 chip, or an HCT00, or even a regular old 7400 if you're being totally old school. So that's how we want to do it, and I think that probably makes this video long enough. I've been yapping a long time, so I appreciate you all joining me. We will actually wire this up. Actually, we won't wire it up next time. Now that we know what our memory map is going to be and how we're going to implement our memory map, I think we'll write the software next. So that'll be the next video. And then once we get the software written, we will burn it onto this ROM and wire everything up and see if the magic smoke comes out. I am looking forward to it, and I hope you gentlemen are as well. If you've made it this far, thank you, sirs, for joining me. Happy Z80 Funtime Day. I'll catch you next time, boy.